we are going to learn about exponential growth and decay. And in order to do that, we need a formula as a baseline to help us calculate these things. So this is the formula for exponential growth and decay. It's y equals a times 1 plus r to the t power. So a represents your starting amount. Whatever it is that you are going to be starting with goes there. Your R represents the rate of either growth or decay. So if your R value is bigger than 0, it means that there is growth because you are adding more than 0 to whatever you're starting with. If your R is less than 0, it indicates decay because you are subtracting from your initial amount. Anything that's less than 0 is negative. So if you have a negative number there, then you are looking at something decaying or getting smaller. Keep in mind that you will see rate as a decimal, but we usually talk about rate as a percentage. So here we always start with 1. 1 represents 100% of something. So as we determine a rate, whether it's growth or decay, we're going to take whatever percentage that is and turn it into a decimal, and you'll see that in just a little bit. Finally, t represents time, how much time is going by. Typically, you will see this in years, but sometimes there are other units of time. They're specified. So if they're not specified, you can assume that years are going by, but if it says months, then you can think of t in terms of months instead. So here is an example of this formula in action. There we go. So we want to see if we are looking at growth or decay when we are looking at these equations. So starting with this example, y equals 67 times 1.06t, or to the t power. Is this growth or decay? Well, remember your original formula has your starting amount and then 1 plus whatever your rate is to the t power. So here we can see that this has gone bigger than our original 1. How much bigger is it? 0.06. So we have growth here by a factor of 0.06. Now that is as a decimal, but remember, we talk about growth in percentages. If you went to the bank and they told you you were going to have a 2% interest rate, they wouldn't say 0.02, they would just say 2%. So how do we think of growth of 0.06 as a percent? We move the decimal place over 2 places. We go 1, 2, and that is 6%. So this is 6% growth for this problem. Let's try another one, very similar. Y equals 98, that's our starting amount, whether it's dollars in the bank, whether it's bacteria in a petri dish, whether it's people living in a certain town, that's the number of things, items we're starting with. So we've got 98 times 0.87 to the t power. So again, let's consider our base equation. Our a is what we're starting with, and 1 plus r to the t power. This value right here has taken our original 1, which is 100% of something, and it's made it smaller. How much smaller has it made it? Well, we are looking at a decay of 0.13, and I got that through subtracting. We start with 100%, and we're taking away 87%. So how much of a decrease was that? A 13% decrease, which is why we are experiencing decay at a rate of 13%. Some things that experience exponential decay are cars. If you've ever heard a car loses its value the moment you drive it off a lot, that's because its value is decaying exponentially. Probably a different rate than 13%, but that's just an example of decay in real life. Let's look at this third one. We've got y equals 300 times 1.27 to the t power. So we look at this number and we ask, is this bigger or smaller than 1? Keeping in mind that 1 is the same thing as 100%. This is just two different ways to look at it, as a decimal or as a percent. So this is definitely bigger than 100%. Specifically, it is 27%. So we say that there is 27% growth. I said that all messed up. 27% growth. Because it is 27 more, or 0.27 more than the 1 that we started with. We're just converting to percent. Let's try this last one. This is a lot of decay here. Oh, it's not the last one. Sorry, full of lies. How do I get another page? Hold tight. There we go. All right, we got a new page. So if we write down the problem, it's y equals 142 times 0.35 to the t power. Is this bigger than 1 or smaller than 1? It's way smaller. Specifically, if we subtract this from 1, if we do 1 minus 0.35, we will get that there is a 0.65 rate of decay. And as a percentage, that would be 65% decay. So y equals, last one, 5 times 2 to the t power. How much bigger than 1 is 2? If we think about our original form, 1 plus r to the t power, what does r need to be so that this whole thing adds up to 2? Our r needs to be 1 because 1 plus 1 makes 2. As a decimal, that means that there is a rate of 100% growth. A rate of 100% growth means it's doubling. It goes from 100% to 200%. So when things are multiplying at a very fast rate, when they're doubling, you could get something way bigger than 1 in here, and that's okay. So this started with 100 and it jumped to 200%, and that's why it's 100% growth. Because we started with 100%, that's this right here, and then we added another 100%. That's where that 2 came from. 2 is just a decimal that means 200%. So we need to know this because we can apply this formula to word problems. These word problems are going to be a little bit dated. They might seem a little bit silly because some of the numbers are made up, but you can at least appreciate the fact that there are some real life applications here. These are some things you might want to calculate because they have to do with money, and that's something that's important to you. So for this example, you're selling your old iPad on Craigslist. After doing some research, you discover that a value of an iPad decreases at a rate of 35% annually. So we've already learned that this is a decay problem because the value of your iPad is going to get lower. If the original price of your iPad was $500, at what price should you list your iPad if the device is 5 years old? So remember, our base formula for this is y equals, and y is how much you're going to get at the end. That's your starting amount times 1 plus r, which is your rate, to the t power, which is the amount of time. So let's do it. We don't know what we're going to end up with. Our whole goal is to figure out what we need to sell this iPad for at the end. So we don't know. So we're going to leave this as y. But we do know what we're starting at. Our starting value of our iPad is $500. Now, we know that there is decay happening here. Specifically, it's happening at a rate of 35%. So we know that we need to subtract that value because whatever's in the parentheses needs to be less than 1 to show we're getting smaller. So we're going to subtract 0.35 because that is 35%. We just wrote it as a decimal, so it'll work with our formula. And then how many years, what is the amount of time that we're going to have this iPad? We've had it for 5 years. So we are going to put 5 up there in parentheses. Sorry, I'm all over the place. There we go. We're going to put 5 up there above the parentheses. So now is the straightforward part. You will put this into your calculator. So what you can do at this time is open Desmos, or you can use your favorite graphing calculator. It doesn't matter to me. But we're going to put that right in there. So we're going to say 500 times 1 minus 0.35. And again, we're doing minus because it's losing value to the 5th power. That lets us know that at the end of this 5-year period, still writing in highlighter, yikes. At the end of this 5-year period, that we can sell the iPad for $58.01. That's one heck of a decrease. That's kind of a bummer, but at least you got 5 years of use out of your iPad. So that's how we do these problems. We use the formula to help us figure out how much something is worth or how many things there will be at the end of a certain amount of time. So this one's a little bit sad. The 100-acre wood is being destroyed to make room for a high-end apartment complex. Suppose the acreage of forest is decreasing at a rate of 2% annually. So we got another decay problem. If there's currently 100 acres of forest, how many acres will Winnie the Pooh be able to play in after 6 years? So we're going to use our formula. Our ending amount is equal to our starting amount times 1 plus our rate to the amount of time. Now, we know that we want to find our ending amount. Our starting amount is 100 acres. And since this is decay, then our rate is going to be negative. That's because the 100-acre wood is getting smaller. So we are going to subtract 2%, and we do that by converting it to 0.02 as a decimal. Then 6 years are going by, so we're going to raise it to the 6th power. So starting with 100 acres, decaying at a rate of 2% over a 6-year period. Now we evaluate this in our favorite graphing calculator. So head over to Desmos and let's plug it in. 100 times 1 minus 0.02 to the 6th power is 88.58 acres. So that is how much land Winnie the Pooh will have to play in after 6 years, 88.58 acres. Okay. You are investing money in order to afford the $500 PS5 you've always wanted. You decide to invest $250 in an annual rate of 4%. Write an equation to model out the return on your investment. How many years until you can afford the PlayStation 5? So this question is a little bit crazy because it's not asking how much money we'll have at the end. We know how much money we want at the end. We want $500. That's our goal. The difference is what we don't know is how long it's going to take. So this problem is a little bit different than the first two we did because there's a different thing we want to know. This time we know the end of the story, we just don't know how much time it's going to take. So when we think about our equation, y equals a times 1 plus r to the t. We this time know at the end we want $500. And we are starting by putting $250 in the bank. Now, our rate is 4%, and we are adding that because we better be making money when we put it in the bank. If you put your money in the bank and you lose money on it, that's not great. What we don't know is time. So that's what we're going to be solving for. Now, First thing we can do to get t by itself is to isolate the base and the exponent. We want to get that alone, and we can do that by dividing both sides by 250. So we're going to divide by 250 over here and divide by 250 over here. And we will get that 2 is equal to 1.04. I went ahead and just did this together to the t power. Now, t is in a different spot than we've been used to solving in the past. But this unit, we've learned a new skill to help us figure out what an exponent should be. The undoing, the inverse of an exponent is a log. So we are going to rewrite this as a log. Now, remember our goal is always to get whatever the exponent is alone. Our goal is to solve for the exponent. So that's what we're going to write first by itself, t. We want to get t alone. Our log goes next, and because the base is 1.04, we're going to make that the base down here of 2. Now we can put that in our graphing calculator, and we can type in log with a base of 1.04 of 2, and we end up with 17.67. And t, remember, represents time, so that is the number of years it will take for your money to turn from $250 to $500. So, do you want to go through with this plan of putting $250 in the bank and waiting almost 18 years to get $500? That seems kind of crazy, right? So maybe this isn't the plan to go with. But what this problem did is it told us how long it will take us for our $250 to turn into the $500 we want if we put it in the bank. There's the bank at an interest rate of 4%. So maybe we need to get a job and earn some money right away, because we're not trying to wait 18 years to get the PS5. It's going to be the PS17 at that point. All right. Oops, I went too far. No, I didn't. Okay, so there's something called half-life. Half-life is a special kind of decay. You may or may not have heard of radioactive substances. If a radioactive substance is sitting there, as time goes by, something crazy is going to happen. Let's say a radioactive substance has a half-life of 1 year. What that means is when the first year goes by, it's going to cut in half. That's why it's called half-life, is because the substance literally cuts in half. So in year 1, it cut in half. Then another year goes by, cuts in half again. Then another year goes by, it cuts in half again. And then another year goes by, it cuts in half again. Another year goes, okay, so you get the point. As the years go by, the substance will cut in half and in half and in half and in half and in half. Some substances decay like that, but they do it at a different rate. So this was the yellow substance, substance A. But what if we have substance B, and it's radioactive, it decays, but what if it does it at a slower rate? What if it decays at a rate of 5 years? Okay, so 5 years goes by, and it cuts in half, just like substance A did. The difference is, over 5 years, this guy has cut in half not just once, but 5 times. 1, 2, 3, 4. There's going to be very little left of it. So even though both substances are radioactive, they have different half-lives. A half-life of 1 year means the substance cuts in half every year. A half-life of 5 years means the substance cuts in half every 5 years. The substances are still going to cut in half. They're still going to decay. They're still radioactive. So here is a formula that you can use to model half-life. Y equals 0.5. The reason we have 0.5 in there is because this means the 100% that you start with minus the 50% that gets taken away each half-life. So every half-life, you start with 100% of the substance, you take away half of it, that leaves you with half left over. And then we raise it to the t power for time. But then Remember how these substances had different half-lives? This one had a half-life of 1 year. This one had a half-life of 5 years. We account for that by taking the amount of time and dividing it by whatever the half-life is. And we use the letter N here to indicate the half-life. That way, if 5 years goes by, we can tell the difference between our yellow substance, which decays faster, and our pink substance, which decays slower, by putting that rate of decay, that half-life, into our equation. So if we look over at the lesson, we can see an example of half-life with dots. You can see we're starting with a full grid, and then as a year passes, the number of dots cuts in half and in half and in half and in half. So that models decay. And the percentage the substance cuts in half each year is 50%. That's just half. So we're going to look at some half-life problems. So here is a half-life problem about the pesticide DDT. So DDT, just like the other things we talked about, if you have a block of DDT, it's going to sit there and decay. Now, what we see in this problem is DDT has a half-life of 15 years. So that's a much longer half-life than the substances we talked about in yellow and in pink. It means that it's going to take 15 years for it to cut in half. And then it's going to take another 15 years. So after 30 years, it's going to cut in half again. So it's happening pretty slowly. So we've got our block of DDT. Trying to make it come back. There we go. Okay. So a scientist obtains a 100-gram sample of DDT. And we want to figure out how much DDT there's going to be in 45 years. So let's write an equation. Y equals A times 0.5 to the T over N. And we know 0.5 is always going to be here because half-life is literally the amount of time it takes for something to cut in half. Now, the starting amount of DDT is 100, so we're going to put 100 in the start position. How much time are we looking at? We're looking at 45 years. But this doesn't cut in half every year. It's not going to cut in half 45 times. It's only going to cut in half every 15 years. So we want to take that 45 and divide it by the half-life of 15, because what that means is it's going to cut in half 3 times. That was a weird little squiggle. But it's going to cut in half 3 times over this time period. How many 15s will fall into 45 years? 3 of them. So you can just leave it like this, but what this means is it doesn't cut in half 45 times. It cuts in half every half-life. So every group of 15, it cuts in half. Now, some of you might be saying this part is wild to me, and if that's the case for you, I've got a backup plan. For now, hold that thought. Let's head over to Desmos and calculate the half-life based on the information we have. So 100 times 0.5 raised to the 45 divided by 15 gives us 12.5. So that means that we will have 12.5 grams of DDT after the time period of 45 years has gone by. So if you're saying, yo, I'm not here for this equation, I don't like it, I've got a backup plan for you. Let's make a table instead. And in the top, let's put years. And in the bottom, let's put how much DDT there is in grams. At the very beginning, after no time has passed, there was 100 grams of DDT. We know every 15 years, DDT cuts in half. So after the first period of 15 years, how much DDT is there? 50 grams. After the second period of 15 years, after 30 years, how much DDT is there? What's half of 50? 25 grams. After the next half-life, after 45 years have passed, how much DDT is there? Cut that 25 in half, 12.5 grams. And we did it. The problem says, how much DDT will there be after 45 years? Well, we can just look at the chart we made and say, hey, at 45 years, there'll be 12.5 grams of DDT. And we did that simply by recognizing every half-life, we cut the amount of DDT in half. So if you prefer to use the formula, use the formula. That's fine. You'll get 25 grams of DDT. Or sorry, you won't. You'll get 12.5 grams of DDT. And if you prefer using the table, you'll also get 12.5 grams of DDT. It doesn't matter to me as long as you are comfortable with what you're doing. So let's try this one. Plutonium has a half-life of 6 hours. So that means every 6 hours, plutonium cuts in half. How much plutonium will remain after 1 day? So our formula is Y equals our starting amount times 0.5 to the T over N power. Remember, N represents that half-life doesn't necessarily happen every year. It happens as often as we are told. So for this problem, we are actually not going to be operating in years. We're going to be operating in hours. And that's because we are told the half-life of plutonium is 6 hours. So Y equals our starting amount, 5 milligrams of plutonium. You don't have to put mg in your sample. I should have just written the 5. There we go. Okay, so 5 times 0.5. And then how much total time are we looking at this plutonium? 1 day. How many hours is that? 24 hours. But it's not going to cut in half 24 times. It's going to do that every 6 hours. That's why we divide by 6, so we can recognize it's going to cut in half every 6 hours over a 24-hour period. Put that into Desmos, and it's going to tell you how much plutonium will be left. So 5 to the 0.5, or sorry, times 0.5 to the 24 over 6. And you end up with 0.3125 milligrams of plutonium. Now, if you are a chart person, let's start with hours and then plutonium in milligrams. At 0 hours, you have 5 milligrams of plutonium. We know every 6 hours, this number is going to cut in half, so this becomes 2.5. At 12 hours, it's become 1.25. At 18 hours, I can't do that off the top of my head, but we're going to use the calculator. It's become 0.625. And at 24 hours, it's going to become 0.3125. And that's what the problem's asking for. After a day, after 24 hours, how much is left? So whether you use the chart or you use the equation, it doesn't matter. You're going to get the same answer. What I want you to notice is how many times the substance cut in half. It cut in half 1, 2, 3, 4 times over the course of the day. That's why we do this right here, because 24 over 6 is 4. That represents that it cuts in half 4 times over the course of the day. So that's why we have to divide by 6. Not because it's cutting in half 24 times, but 4 times over the course of the day. All right, last one. And this is a great one for you to try, so I suggest pausing the video here, but if you would like to see how it's worked out, you can work on the problem and then hit unpause and it'll come back. All right, here we go. Let's talk about it. So our equation is Y equals A times 0.5 to the T over N. And in this case, we have a half-life of 2 days. So our ending amount is going to be our 600 gram sample times 0.5. How much time? Well, we don't know. This problem's a little bit different. Wait a second. We want to know how many days. So this problem's a little bit different. We know the ending amount. The ending amount is told to us this time, so we're going to come at this in a different way. We want to know how long until we have 18.75. So we actually know our ending amount. We know our ending amount, we know our starting amount. What we don't know is how much time it's going to take. We also know that the half-life is 2 days, so we do know to put a 2 right here. Well, we can use the skills we know to find our exponent. First thing we have to do every time is get this little exponential piece by itself. So we're going to divide both sides by 600. Divide by 600, divide by 600, and we end up getting 18.75 divided by 600 is 0.03125, and that's equal to 0.5 to the t over 2. Now, we know to get an exponent by itself, we rewrite it as a log. So t over 2 is our exponent, equals log. The base is 0.5, and we're finding it of 0.03125. So we can type that in our calculator, log base 0.5 of this guy right here is 5. So t over 2 is 5. And we can finish, how do we undo division by 2? Multiplying, so t equals 10. So the amount of time in days is 10. It will take 10 days in order for it to go from 600 to 18.75. Now, you can still use the chart for this, so let's do it. We want to know how long it's going to take. So remember, at the beginning, we have days, and at the bottom, we have the grams of uranium. So 600 grams of uranium at 0 days. We know every 2 days it cuts in half. So after 2 days, 300. After 4 days, 150. After 6 days, 75. After 8 days, 37.5. And after 10 days, 18.75. So we can see by doing it this way, this time we're looking for the days, it takes 10 days to get to 18.75. Either way, you'll end up with 10 days, so it doesn't matter to me how you do this as long as you are comfortable with what you choose. So here's a place for you to give a little feedback on today's lesson, and thank you so much.